exponential. So exponential distribution brings another dimension again. So this is similar to the Poisson. This is other side of looking at the Poisson process or the Poisson distribution, okay, from the analog side. So this is used for modeling the amount of time until a specific event occurs, okay. So this will give me the amount. This is used to model amount of time, okay, until I'll give you some examples to make it clear. Specific event occurs, so the time factor comes in, similar to what we saw in the Poisson distribution. So what is there? So this is used for, okay, this is used to model all the events that are happening at a constant rate, as was the case in Poisson distribution, and those events are happening due to some random reason, not due to wear and tear, okay. Let me give you an example. For example, so what will be the time between, earlier in Poisson we saw number of customers. Here, if you want to model what will be the time difference between two customers. So you have got one customer. Now when will the next customer come to the store? If you want to model this, then we use exponential distribution, okay. Time between customer arrival at store, okay. Another example is with respect to electronics items, okay. So the lifespan of electronics items, what will be its lifespan? That, okay, that because electronics part don't wear out, they fail just randomly. So for modeling such kind of events, we use exponential distribution. So we model like lifespan of a electronic item that does not wear out. Okay, if it does not wear out, then we can use exponential distribution to model the behavior, that if it has, means when will it fail next, okay, or when the customer has come in, when the last customer came, when will the next customer come, okay. That can be modeled using exponential distribution. It is just another phase of the Poisson distribution. I will make a video that will compare Poisson and exponential distribution. In the next video we'll discuss about that, but let me give you the parameters. The parameters are similar to what we have seen in Poisson. What are the parameters for getting for the Poisson PMF, or for the exponential PMF? So there is one rate parameter, similar to what we had lambda, rate parameter, that is lambda. This is the average number of events per unit time, similar to the lambda of Poisson end, okay, Poisson distribution. And then there is another thing which is called scale parameter. The scale parameter is given by beta or also mu, that is mean, okay. This is the mean time, that is the mean time between events. So what are the parameters? Lambda and mu. And what is the relation between this? If we know average number of events per unit time, then we can find the mean time between events, that will be reciprocal of each other. Lambda is equal to 1 by mu or 1 by beta, same thing. And what is the PDF? PDF of this is given by f of x is equal to lambda into e to the power minus lambda x for x greater than 0 and lambda lambda greater than 0. The average number of events is greater than 0 per unit time. We also know the CDF of this. If we integrate this, this will command. So we know that this is capital F for CDF and this is small f for CDF. So if you know the PDF, we can integrate this and this will come to 1 minus e to the power minus lambda x. Okay, same thing for x greater than equal to 0 and lambda greater than 0. See, if we differentiate this, we'll get the CDF. This will become 0 and this will become, lambda will come here, lambda e to the power minus lambda x, and this is your CDF. Okay, so let me highlight this for you. Sorry. Okay, so let's solve a problem to understand this, and with this we'll end that exponential also question. So what is the question? So if we go to a bank and on an average a teller spends 4 minutes for a customer. Now what is the probability that a selected customer will be served in less than 3 minutes? So if you go to a bank, there's a teller who takes on an average 4 minutes per customer. What is the probability that a customer will be served in less than 3 minutes? Okay, let me write it down for you. So what is the problem? At a bank, a teller who gives money, okay, spends 4 minutes. I know they take even longer, but for the problem's sake, on an average with each customer. Okay, now I know that they take 4 minutes on average. So now if I want to model or find out what is the probability that the any random customer, that a customer who walks in will be served in less than 3 minutes. So what is the probability of getting served in less than 3 minutes? Means either that customer can be served in 0 minutes or 1 minute. 0 minutes not possible, right? So anything between 0, 1, 2, or any number less than equal to 3. All the numbers which is there between 0 to 3 minutes, right? So we want to find, this will not be discrete. These are the discrete values I was giving you for reference, but this is not possible because we have a range of number. It can be any value between 0 to 3. So anything between 0 to 3 minutes are all the possible values that it can take, and that's why it's a continuous. So between 0 to 3. So what do? We integrate the PDF from 0 to 3. So, and we get the CDF. So we have the CDF formula already here. We'll use this. Okay. So the CDF is, what does the CDF give you? CDF is equal to f of x is equal to probability of x less than equal to x. Here it is 1 minus e to the power minus lambda x. Okay. So what do I want to find? Probability of a customer getting served in less than or equal to 3 minutes. This is equal to 1 minus e to the power minus lambda x. What is lambda? Let's find out lambda. Lambda is our rate parameter. So what is the rate at which the teller is serving? They are serving on an average 4 minutes. Okay. So on an average, so I have got my rate parameter, right? I have got skill, mean time between events. Okay. Mean time between two customers is 4 minutes. So I've got the mu. Mu is equal to 4 minutes. Between two customers, on an average, it takes 4 minutes. So that is the mean time to serve one customer. So what will be my lambda? Lambda is equal to 1 by mu. That is equal to 1 by 4. That is equal to 0.25. Okay. And x is equal to 3. Now let's put this in the equation. X less than equal to 3. That is equal to 1 minus e to the power 0.25 into 3, right? is equal to 1 minus e to the power minus 0.75. This is equal to 1 minus e to the power minus 0.75. What is the value? Let me check. E to the power minus 0.75. This is equal to 0.4723. 0.4723 something something something. Okay, so this is equal to, what will be the value? 47 means 43, let it be 53. 0.53. So in percentage terms this will be equal to 53%, right? Let me move it from here. So here, let me show you again. So 1 minus 4723, this is 0.53, means in percentage terms this will be 53%. So on an average, the delay took 4 minutes and the probability of serving a customer in less than 3 minutes is 53%. This is our answer, or 0.53, sorry. So I hope our this thing, exponential distribution, is also clear. It is similar to the Poisson distribution. So I'll leave you a question to solve, practice. So what will be the probability that a customer will be served in greater than 2 minutes? What is the probability that customer is served in greater than 2 minutes? I'll leave you to figure this out. But there is some minor manipulation to figure this out. I'll leave this question. Try it out, okay? And I'll leave you the answer here. The answer here would be equal to 0.6065 to be the answer. Try it out, okay? Try this.